So now for our last example in this unit, we're going to look at one more wrinkle in these simplex method problems, which is what to do whenever you have a constraint that has equality. So we've seen what to do whenever you have a standard constraint or an inequality that faces the wrong way. For that one, you would use a surplus variable. So you would need to subtract a variable from that left side. And now we'll see what to do whenever you have an equal sign in one of the constraints. So I would encourage you to read over this example that's typed up. It fully works this problem up at the top of the page, but I don't think that that's especially instructive to do in the video. It'll be easier for you to just read through this on your own. But I will talk about what's new in this example, which is this equality constraint. So how do we handle equality constraints? Well, unfortunately, this simplex method approach that we've been using requires a new variable for each of our constraints, even if they are equalities already. So you might be thinking that this would be nice and easy because we already have an equal sign there, and that's what we were using these surplus and slack variables to attain. But unfortunately, our constraints, just for a technical reason, have to add a new variable to each line here. So each new constraint needs to have its own variable. So we will add a new variable to that equality. So notice that this is the same equation that we have up at the top here. It's just that I've added what's called A1. Now notice that if I wanted to satisfy the original equation up at the top of the screen here, I would need A1 to just be 0, because I already want this equation to be true with A1 gone. So I want A1 to be 0. And that's why we call it an artificial variable. It's artificial because we know that we want it to be 0, otherwise we won't be satisfying the original equality. But unfortunately, we have to add a variable in order for this approach to work. So we'll add an artificial variable, and the artificial variables will always go to the right of the slack variables and surplus variables. So whenever we build our matrix, the artificial variables will come over here to the far right, past all of the slack variables and so on. So we will look at building this matrix using this artificial variable, and then we'll talk about how to pivot using these artificial variables. So the initial matrix will look like this. The only new thing is that your artificial variable will come over here to the far right. And now we need to talk about pivoting. To pivot, we will always start by fixing the artificial variables first. So just like we wanted to fix the negative surplus variables, so notice that in this case S1 is equal to negative 300. So we will want to fix that in phase 1. But in phase 1, we also need to fix the artificial variables. The artificial variable right now is valued at 200, but it's supposed to be 0. So we will use phase 1 pivoting rules to fix the artificial variable. And we're going to keep trying to fix this artificial variable until it becomes 0. And then once the artificial variable is 0, you can move on to the rest of phase 1, which we've already talked through. So the only new thing is that for this artificial variable, I need to use phase 1 pivoting rules to fix the value of the artificial variable to be 0. And I just keep using the phase 1 pivoting rules until A1 is equal to 0. And remember that the phase 1 pivoting rules say you look at the indicator, or the coefficient, I should say, that you're trying to fix. So in this case, this 1, you look to its left, and you choose the largest positive value that you can to the left here. If there are no positive values to the left, then that just means that there is no optimal solution. So you can be immediately done with that kind of problem. But here, you would look to the left and see any positive values. You choose the largest one, and that tells you what your pivot column would be. So we know that our pivot column is the one that has this 20 in it, and then we would compute these quotients like we've done over here. And we choose the smallest quotient. The smallest quotient is 10. That tells us our pivot row. And when I put those together, I get that our pivot in this example would have been 20. So you can see what the rest of the procedure looks like. if you want to read through this example. But the important thing is that once an artificial variable is non-basic, like it is here, we can actually just delete that column entirely from the matrix. So as soon as you've turned that artificial variable to 0, it's never going to change away from 0. So once the artificial variable hits 0, it's going to stay 0 for the remainder of the problem. For that reason, we normally just delete that column altogether. So you'll notice that in the next matrix, there is no artificial variable. That's because it's done its job already. So once the artificial variable is 0, we've made it into the feasible region, at least for that artificial variable, and we can just delete the artificial variable from the matrix. Now, in this case, we do still need to continue with phase 1 because we still have a negative surplus variable. So you might not be done with phase 1, but we've at least fixed the artificial variable. And then we can move on with fixing this negative 1. And to do that, we would just use the ordinary phase 1 approach, and then after that, you can use the basic simplex method. But notice that in this particular example, after phase 1, you don't have any negative indicators. So you're also immediately done with phase 2, and you can just read off the solution. Okay, so let's talk through an example like this. So here we're trying to solve this linear programming problem. We want to maximize P. Now you do have to start paying attention to whether this is a maximization or a minimization problem. So because this is a maximization problem, this is pretty standard. But if it were minimization, we would have to use the negation trick that we talked about right before this problem. But here it's an ordinary maximization problem subject to this list of constraints. So we have two non-standard constraints. We have an equality constraint, and we also have an inequality that faces the wrong way. So I'll go ahead and write the equations that we would need here. As you start to get comfortable with these problems, I don't expect you to write down all of the equations. I would be fine with you just jumping to the initial simplex tableau. But for now, let's rearrange this equation. So I'll rearrange the objective equation so that it looks like negative x1 minus 4x2 minus 2x3 plus your objective is equal to 0. And then we also need to write the correct equations for our constraints. For our first constraint, I have x2 plus x3 plus my first slack variable is equal to 4. So that's an ordinary constraint, so we'll just need to add a slack variable like we have been doing. Our second constraint is a little bit weird, so this one is x1 minus x3. This one is an equality constraint, and therefore we need to add an artificial variable. So we'll add a1 equals 6. And then for this last one, this is a non-standard inequality, so we'll need to subtract a surplus variable. So for that last inequality, we'll have x1 minus x2 minus x3 minus a surplus variable, and that will equal 1. So these will be our constraint rows, and then our objective row comes from that top row there. So I'll write the initial simplex tableau here. So let me start by just labeling the columns. So we'll have x1, x2, x3, and then we have two surplus or slack variables. And remember, the artificial variable will go on the far right here, and it will be deleted as soon as we manage to turn it into a 0. And I'm going to suppress the ordinary P column, which would be 0, 0, 0, 1, and instead I'm just going to write P and identify it with this bottom right value. So let's translate each of these constraints into equations here. So for that first constraint, I have an x2 plus an x3 plus an s1 equals 4. So that would look like this. For the next constraint with the artificial variable, I'll have a 1, a 0, a negative 1, whoops, and then a 0, 0, 1, 6. So there I am actually using my artificial variable. And then for the last constraint, I'll have a 1, negative 1, negative 1, 0, negative 1, 0, 1. So those are our constraints. And then lastly, we'll write the objective row. So that would be a negative 1, a negative 4, a negative 2, and then zeros. Because remember, we're not recording the coefficient on P, we're recording this number on the right. So this is our initial simplex tableau. And now notice that the value of A1 is equal to 6. So that means we're in phase 1 right now. So we're in phase 1. We need to be fixing the artificial variable. Phase 1, if you have artificial variables, phase 1 will always start with fixing the artificial variable. So you always do artificial variables first, and then any negative surplus variables. And then after that, you can move into phase 2. So we're using phase 1 rules. That means that I'm looking to the left of the one that I want to fix, and I find the largest positive value. In this case, there's only one positive value over here. So that tells us our pivot column. And then to compute the pivot row, I need to compute those quotients like we have been doing. I do that for any positive values that live above the objective row in this column. So in this case, I just have 2 of those. I'm going to compute quotients for each of those. That would be a 6 over 1, which is 6 here, and then a 1 over 1. So 6 over 1 would be 6, and then 1 over 1 is just 1. We choose the lesser of these. That tells us the pivot row. So that means that this one is our pivot. Now, thankfully, it's already a positive 1, so we don't have to do any division here. And now we just need to fix the rest of that pivot, column. So to fix the rest of that column, I need to eliminate this 1 and this negative 1. So for row 2, I'm killing a positive 1, so I would just subtract the pivot row. And then for row 4, I'm killing a negative 1, so I would just add the pivot row. Okay, so the top row we don't need to do anything about, so this one is not going to change. For row, well, I'll also write our pivot row again just to sort of fill in the matrix. So our pivot row is also not changing. It looks like this. For row 2, I'm taking the old row 2 and subtracting row 3. So I'm taking row 2 and subtracting what's beneath it, so I would get a 0. Here I would get a positive 1. Here I would get a 0, and then a 0, and then a positive 1, and then a positive 1 again, and then a 5. So that's what I get for the new row 2. And then next for the new row 4, the new objective row, I'm taking row 4, the old row 4, and adding what was above it. So this one would be a 0, this one's a negative 5, a negative 3, a 0, a negative 1, a 0, and a 1. Okay, so now we need to check in. We first check in with our artificial variable. Now notice that in this case our artificial variable is still valued at 5. So we still have that A1 is equal to 5. That means we're still in phase 1. So I'm trying to fix this 1, really the artificial variable. So I look to the left, I look for the largest positive value that lives to the left of this. Now remember that if there's a tie, we're just going to choose the leftmost one. So there are 2 positive 1s here, but I'm just going to take the leftmost one to serve as our pivot column. And now we need to determine our pivot row. For the pivot row, I need to compute the quotients. In this case, I only need to do it for these 2 entries because those are the only 2 positive entries that live in that column. So I would compute the quotients. The quotients in this case are going to be 4 over 1 and 5 over 1. So 4 over 1 is 4, 5 over 1 is 5. The lesser of these tells me which one is my pivot. So this will be my pivot. And again, thankfully, this pivot is just a 1 already. So we don't need to do any division, but we do need to correct the rest of the column. So in order to do that, I will take row 2 minus the pivot row, because I'm trying to kill a positive 1 there. To kill the negative 1 in row 3, I would add a positive 1 times the pivot row. And then to kill a negative 5 in row 4, I would add a positive 5 times the pivot row. So the pivot row is not changing. Still going to look like this. For the second row, we're subtracting what's above it. So this would be a 0, negative 1, negative 1, 1, 1, 1. For row 3, I'm adding row 1. So this one would be a 1, a 0, a 0, a 1, a negative 1, a 0, and a 5. And then for row 4, I'm adding 5 times row 1. So this would be a 0, this one would also be a 0, this one is a negative 3 plus 5, so that would be a 2. This one's a 0 plus 5, this one's a negative 1, this one's a 0, and this one is a 1 plus 5 times 4, so that's a 1 plus 20, which is 21. Okay, so here's where we land. And now we need to check in again with our artificial variable and also with any surplus or slack variables just to make sure that they're non-negative. Now notice that our surplus and slack variables, those are already non-basic, so both of those are 0. So we're happy with those, but unfortunately our artificial variable is still not fixed. So our artificial variable is equal to a 1. And therefore, we're unfortunately still in phase 1. So phase 1 rules, we look to the left of the artificial variable, we choose the largest positive value that we can. Now in this case, there's only 1, so this must be our pivot column. And now we need to determine the pivot row. But for that, we look at any positive values here and compute the corresponding quotients, but there's only one positive value here, so this must be our pivot. You could compute the quotient if you wanted to, you would just compute 1 divided by 1, which is 1, but you don't really need to compute that quotient if this is the only candidate. So this will be our pivot. And now I need to eliminate any of the values, any of the non-zero values that remain in the rest of that column. So I think what I'll do here is I'll just decide what the row operations should be, and then I'll show you what the resulting matrix is. And you can just trust me on that one since we're out of space on this page. So we need to fix these two entries. In order to do that, I would take row 3 and add the pivot column, the pivot row. And then I would take row 4 and add the pivot row. So for both of these, I'm just adding row 2. And now you can just trust me on this next row operation since we can't really do it side by side with the current matrix. So what we'll get as the resulting matrix is this. So the top row is not going to change. Still looks like this. The second row is also not changing. So it looks like this. But these bottom 2 rows are changing. The new third row looks like this. And the new objective row looks like this. Okay. So now let's relabel our columns and then reassess where we're at. So we have x1, x2, x3, and then our surplus and slack variables, our artificial variable, and then p, the thing that we were trying to maximize. Okay, so now we need to check in to make sure that we're not in phase 1. So let's think about what the value of A1 is. Notice that A1 is equal to 0 because it's a non-basic column. So we can actually just delete this column altogether now that A1 is 0. Now we also have that S1 is equal to 0 and S2 looks like it's equal to 1. So none of these are negative, which means that we're no longer in phase 1. So that means that we've moved on to phase 2, and now we can just treat this like an ordinary simplex method problem. So I can delete this column, and now I can just look for, look here. So we'll delete the artificial variable column, and what will be left is this matrix that has this objective row. And notice that this objective row doesn't have any negative indicators. So we're actually already done. And therefore we can just read off the values for our variables because we've found the optimal solution now. So we'll do that. Remember that when you read off the values here, we ordinarily don't report the values of the variables that we introduced artificially. So the artificial variables are surplus or slack variables. Instead, we're just going to report the values of x1, x2, and so on. So, and maybe it'll be good to do this in a different color again, just so that I can actually mark out the columns. I want to make it so that the columns are still sort of legible in case you wanted to check the previous step. But I think it's easier to read the matrix if I do actually mark out the irrelevant columns. So I'll mark those out in red. And now I can read the values of my variables. If I want x1, I would look at this row. I would get that x1 is equal to 6. The equation involving x2 just says that x2 is equal to 4. x3 was non-basic, so its value is equal to 0. And the corresponding value for p, remember we identify p with that bottom right value, so p would be 22. So we'll get a maximal p-value of 22 whenever x1 is equal to 6, x2 is equal to 4, and x3 is equal to 0.